Hello, folks. We're going to look at Chapter 14's environmental homework. So I'm going to look at problems 1, 3, 6, 9, 12. Felt these problems were a little bit more relevant, a little bit more useful, a little bit more easily solvable. So let's take a look. So starting off with number 1. Number 1, based on what you know about the structure of humic material, explain why it's more likely to have a net negative charge than a net positive charge. So we got to think about the effects of basically humic material is largely carbon-hydrogen bonds and types of aromatic rings. Now, carbon-hydrogen bonds are not particularly acidic and they're not particularly basic, and meaning they do not want to accept any protons. So they're going to stay a net neutral charge. When it comes to oxygen bonds, so the oxygens in there typically are going to be in the form of carboxylic acids. Carboxylic acids, by their very definition, are acidic, meaning they exist in two states: the protonated neutral state and the deprotonated charged anionic state. They are less likely to exist as a protonated, double protonated cationic state. So we would not expect them to contribute to a positive charge. And so that is the main factor on the negative charge. Now, nitrogens can be acidic, but they can also be basic. In fact, they're usually more basic than not, because they have this lone pair that can then accept a proton to become a cationic state. However, now here's why we have a net negative versus positive. There's largely a greater amount of oxygen than there are of nitrogen. There's more oxygen than there are nitrogen. Because nitrogen, in the form of amines, typically are present in the humic material from the start. They are a byproduct of a lot of protein degradation, that amino acids are somewhat already dependent, but humic material, as it starts to be consumed and broken down into smaller and smaller parts, we see an increase of oxidation as we're converting carbons to alcohols, which can be deprotonated, and carbons to carboxylic acids, which can definitely be deprotonated. So we're not introducing more nitrogens, but we are introducing more oxygens. And so that leads to this being an overall larger net negative charge than there would be a net positive charge. So that is something we could absolutely do without a problem. It's a thought process, but we have to think about humic material. Now, problem 3. A sediment containing some 47% clay and some 3.2% organic matter is found to have a cation exchange capacity of 10.5 centimoles cation per kilogram of sediment. Assuming the organic matter has 210 centimoles per kilogram, show that the clay could be kaolinite but not montmorillonite. So we have to make an assumption. So of our sediment, we have to assume 1 kilogram of sediment, or some fraction of 1 kilogram of sediment, means we'd have 470 grams of clay and 3.2 grams of organic matter. So 1 kilogram times my 10.5 centimoles per kilogram is going to be, this is the overall capacity, centimoles. This must be equal to CEC clay times 0.470 kilograms plus CEC organic matter times the 0.0032. No, not 0.032, 0.032. So 0.032 kilograms worth of organic matter. So we've been told that's 210. That's 210. So 210 times 0.032 says, well, this is going to be 6.72. That's a contribution of 6.72 centimoles of our 10. So 10 minus the 6.72 leaves like 3.28 centimoles and equals the I'm running out of room. The CEC of the clay times my 0.470. So dividing both sides by 0.470 would give us what is the cation exchange of the clay. So 3.28 divided by 0.47 leads to something like, this value must equal something like, I'm going to round this, 7. It's actually 6.9787, but it's about 7 centimoles of positive per kilogram. Now with that in mind, kaolinite has a range of something like 5 to 10. 5 to 10. Let me check my 3.2 times. Okay. Oh, it's 10.5. I'm an idiot. 10.5. So the 10.5 means that's going to be 3.78. That doesn't change us by much, but it changes up to 804. 804, still well within kaolinite's range. Kaolinite between 5 and 10 centimoles. Montmorillonite is usually between 50 and 100 centimoles per kilogram. So this, while it doesn't have to be kaolinite, there's other clays that have similar CECs. Montmorillonite would not likely be that clay. So that is problem 3. Problem 6 is use the figure 10.1 to suggest how phosphorus release could occur from buried iron-rich sediment. So I'm going to jump real quick, assuming this will work, to my Excel. So use this figure to suggest how phosphorus could be released from iron-rich sediments. I've included both graphs. The idea that, so we got to think about iron-rich sediments. Iron can bind to phosphate. Phosphate can bind to the iron surface of insoluble iron sediments. Insoluble iron-rich sediments. Now, Now, so that's when you get the iron 3 plus, iron oxide. Now, with that in mind, so we could form structures that look like this. I'm going to jump back to my .chem real quick. So essentially, the surface of the oxides, essentially we have the irons bound here, and when we add phosphate, essentially we can bind the phosphates to the iron, O, P, O, and they can bind semi-permanently to the surface and become a strong binding site. Now, this occurs in iron 3 plus, or insoluble iron 3 plus. Now, going back to my Word document so we can see this. Well, in submerged soils typically have low oxygen. So low oxygen content means, so submerged soils have a pH 4 to 6, 4 to 7, kind of like that, and they have low oxygen content. So what's going to happen in those submerged soils where the oxygen gets consumed, the iron dissolves into iron 2 plus aqueous. And so when that iron dissolves, it takes the phosphates with it. The phosphates dissolve as well, and so they become released as the oxygen content goes down and the iron gets reduced to iron 2 plus. Now, part B, in the laboratory experiments, it has been shown that phosphorus is released from sediment under dark conditions, but accumulated in sediment when it's exposed to light suggest an explanation. So we got to think about how phosphorus is used in the environment and what relation is this process to light. And think about how the reverse of this process would occur in the dark. This one's a lot harder of a thinking. But in light, algae can produce oxygen. Producing oxygen favors the formation of iron, an oxidized iron hydroxy, in which phosphorus can be bound. In the dark, microbial decomposition favors reducing conditions, where it consumes all the oxygen generated, and so iron 3 plus and phosphorus become released. So photosynthesis is what binds the iron, and microbial decomposition is what releases the iron. So we're going from oxidizing to reducing conditions, from mildly basic to acidic conditions, all of this, which is binding and releasing phosphorus. So that's a little bit harder. Now, with that in mind, moving directly on to problem number 9. Problem number 9. Problem number 9 asks, the KOW function is frequently used to describe the movement of pesticides in the surface soil pore water, but it is used less frequently to describe the behavior of organic contaminant in groundwater. Explain. The KOW, it's looking at the organic water binding efficiency. Well, soil has a large defined colloid organic matter border. The pore water, we have basically the dirt particles binding together, and we're creating these little pores where water can kind of bind the surface. We got the dirt, which essentially have these little pockmarked holes, little pores in there. So they tend to have a lot of surface area in which colloid, in which we can have some water colloid interaction. While in the groundwater, there might be some sediment bound, but the sediment is far smaller, and there's a lot more water, a lot less colloids. And even then, the colloids the surface colloids where the organic matter can bind is a lot smaller and a lot less effective. So the idea is that there's a lot greater organic matter in our soil, so there's a lot greater binding comparison. So we can still consider our KOW measurements to valid. But in groundwater, the colloids are very minimal, and the organic matter is very low. And so in this case, the comparison is going to be poor. What colloids that are floating are going to be taken with the current. Colloids that are settled, it's going to be a very low interaction. So the basic idea is that the organic matter in soil is high. Organic matter of water, low. And so we can't really look at the organic to water ratio. And lastly, number 12. Number 12 asks us to look at some data. So, look at some data. The data says the solubility in water, S, and the log of KOW values for several pesticides are shown. Using your understanding of the basis of KOW coefficient, you could comment on the relationship between the trends shown here. So with that in mind, I'm going to once again jump back to the word. It'd be easier to show this rather than write it out. So we see DDT, we see parathion, we see atrazine, and we see carbaryl. We see the solubility in water of DDT is very low. The log KOW. So remember, log is a base 10 function. So log KOW 6 means you have a 10 to the 6th. Aldrin, a little bit more soluble, a little bit lower KOW. Parathion, higher, lower log KOW. Atrazine, higher still, lower KOW, log KOW. Carbaryl, very high solubility, much lower log. So the basic idea here is the log KOW is measurement of the ratio of binding to organic matter, or the octanol water partitioning coefficient. So we're looking at how it binds with organic matter, or how basically we're looking at the relationship of organics to that of the organics nature versus polar nature. Having a high log KOW says there's more organic to this, more covalent character than there is polar character. It would much rather interact with the hydrophobic octanol than the polar hydrophilic water. So DDT has a high non-polar hydrophobic characteristic, so it has a very high log KOW. And so because of that, it has a very low solubility. Carbaryl has a much lower log KOW. It still is nonpolar, but it's factors of several hundred, if not 1,000 times lower. So less nonpolar characteristic means it has more of a polar characteristic. It would also equally want to react with water. And so with that in mind, we see an increased solubility. So I mean, that's all it is. If you want to look at this real quick, I've calculated these values into the actual KOW instead of log KOW, and what we have is DDT DDT has a log of 1 times 10 to the 6th. The atrazine, was it? Aldrin first is 6.31 times 10 to the 5th. We have the parathion of 5.01 times 10 to the 3rd. I have atrazine of 3.98 times 10 to the 2nd. And we have the carbaryl of 2.51 times 10 to the 2nd. Just looking at our direct comparisons of the sizes of these. This is about almost a little bit less than 1.5 times smaller. This is about 12.5 times smaller. This is about 126 times smaller. This is about 1.58 times smaller. I mean, and we can see, generally speaking, as these numbers get lower, the solubility gets higher. There's not a nice direct correlation, but there is somewhat of a correlation that we can see here. But that's all. That's all we have for this chapter. So hopefully this has been a little bit informative of how we go about answering these questions. See ya.